Dear students, welcome to this lecture on digital logic and system design. In the previous lecture, we had seen what read-only memory, that is ROM, is all about. So today, we are going to continue with the ROM applications. This is a slide that I saw in the previous lecture also, and I have shown that ROM can be used as the memory or the storage, which is non-volatile in nature. Function implementation can be done using this, and in this sense it combines the advantages of function realization using a decoder and that using a multiplexer, right? In the case of decoder, you need to have external OR gates. As many OR gates you deploy, you're going to realize as many functions out of a decoder. Whereas in the case of a multiplexer, the OR gate is inbuilt, so you don't have to use any external gate, but then only one function can be realized at a given point of time using a multiplexer. But ROM, that realizes, that combines the advantages of both, that is, without putting any external gates you can realize more than one function using the ROM. The other applications are code converter and lookup table and waveform generation. We will see all of them one by one. So let us first see the function implementation using a ROM that we had seen earlier too. So I'm not going to devote much time to function realization. I had shown that how can two different functions be realized using a ROM simultaneously without putting any external gate. What I want you to see is how can the ROM be used as a code converter. In fact, it can be used as a code converter because it is essentially a decoder followed by an encoder. So in this particular example, we are going to see how can a ROM be employed for a BCD to access3 code converter. So we know that this is the truth table for BCD to access3 code converter, whereas where the inputs are 000 and the output is 0011 plus 3, 0 plus 3, 1 plus 3, which is 4. We have seen this code converter before. I'm just repeating the same truth table. So 2 plus 3 is 5, 3 plus 5 is 3 plus 3 is 6, and 4 plus 3 is 7, 5 plus 3 is 8, and so on. 9 plus 3 is 12. So what can we do? We can put these inputs A, B, C, D at the very input of the ROM. Now this 4 to 16 decoder is going to generate 16 minterms out of this 4 input function of 4 input BCD, uh, variables A, B, C, D. So we see that we have to generate the outputs here. So let us consider Z first. So Z is having M0, M2, M4, M6, M8, right? So this is one way to represent ROM. Also, this is called the line diagram, wherein we draw crossing lines, and wherever we put a cross, that means there is the connection, right? So essentially, there will be 16 inputs in every OR gate, 16 inputs, one from each of those minterms, right? So instead of showing 16 vertical lines and 16 fuses here, what we have shown is that what all minterms will be connected to this OR gate input and what all are not connected. So since M0 is 1, I show it connected. M2 is also connected and M1 is not connected, so I'm not showing a connection here. M2 is connected, M3 is not connected, M4 is connected, M5 is not connected, M6 is connected, M7 is not connected, and M8 is connected, right? M8 is connected. Likewise, for Y, M0 is connected, but then M1, M2 are not connected. You have zeros here, right? And then M3 and M4 are connected, so I'm showing a connection here. Then M5, M6 are not connected, I show zeros here. And then M M7, M8 are connected, M7, M8 are connected, and M9 is not connected again. So that will provide the inputs to the Y output. Likewise, M0 is not connected, but then M1, M2, M3, M4, all of them are connected, right? And then M5, M6, M7, M8 are not connected, M9 is connected, right? So, and finally for W, I see that M0, M1, M2, M3, M4 they're not connected, and then M5, M6, M7, M8, M9 are connected. So this will give me the output of the BCD to XS3 port converter. So easy it is. In fact, it will be treated as just a four function realization, right? Four different functions W, X, Y, Z. So that is how I can employ a ROM to realize a code converter. So you give me any input code, you give me any output code, I can realize using the corresponding ROM gate. My only requirement will be how many inputs are there in the code that is to be converted, and how many bits are there in the code that it is to be converted to. Accordingly, I'll have the decoder size and I'll have at least those many OR gates there, right? One thing I would like you to notice, that since BCD inputs 10, 11, 12, 13, 14, 15, they are don't care. So that is why none of these min terms are connected to any of the OR gates, right? So this gives me a clue, which we are going to take as the next topic, that just as we have kept this OR array as programmable, why don't we keep this AND array programmable also? So that will give rise to yet another device which is called the Programmable Logic Array, PLA. We will see it next, but before we move on to PLA, let me look into the other application, the lookup table, right? I give you the example that lookup table, the easiest examples are the multiplication tables, right? I I tried to explain in my previous lecture that 2 threes are 6, right? We know that we can get it by adding 2 3 times, 2 plus 2 plus 2. Similarly, if I say 7 6 are 42, what does it mean? Add 7 6 times, 7 plus 7 plus 7 plus 7 plus 7 plus 7, 6 times, you get 42. But then we memorize multiplication tables so as to make our multiplication task easier. When anybody asks and I have memorized the multiplication table of 7, I can quickly say 7 6 are 42, 7 7s are 49, 7 8s are 56, whatever, right? So likewise we memorize those multiplication tables. So they are basically the lookup tables that are stored in our memories. Similarly, you can have sine table or trigonometric tables. You can have algorithmic. You can have log tables, right? So they're all lookup tables. So over here, I'm giving you the example of multiplication table of 3 as the lookup table realized by a ROM. What are the inputs? You know, since I'm looking at the multiplication table of 3, so 3 ones are 3, 3 twos are 6. This is the multiplication factor and this is the product. Since this is a multiplication table of 3, so I don't have to store 3 all over, right? I simply have to, whenever I give the multiplication factor as input, the product should come out as the output, right? So then it will become the lookup table for multiplication table of 3. So 3 ones are 3, 3 twos are 6, 3 threes are 9, so on, 3 tens are 30. So my inputs are the multiplication factors, which I'll convert to binary. This is the conversion of 1, 2, 3, 4, 5, 6, so on, 10. And the product is given over here in decimal. The equivalent conversion in binary, this is 3, 6, 9, 12, 15, 18. 21, 24, 27, 30, right? So I know since this is going till 30, so this should be represented, the output should be having 5 bits, because 5 bits can have 32 different variations and I just require 30 of them, right? Whereas the input may have just 4 bits, right? Because it is going from 1 to 10, right? So 4 inputs A, B, C, D. These are the inputs A, B, C, D. 4 to 16 decoder I will employ, and then once again E is 1010101010. Correspondingly, using a line diagram, I can show that M0 is not connected, because this will be 000. We do not give in the multiplication table for 0, right? 3 zeros are 0, nobody says that, so I haven't stored it here. So this remains unused, M0 remains unused. M1, it is connected to M1, then M3, then M5, then M7, and then M9. M1 3 5 7 9. In order to get D, it is connected to M1, M2. So it is connected to M1, M2. Then M3, M4 are not connected. M3, M4 are not connected. M5, M6 are connected. Then again M7, M8 are not connected. And then M9, M10 are connected. So I get D. Similarly, I can get C, where C says that M0 is never connected anyway. M1 is not connected because of the 0, but this M1 is connected. M2 is not connected. You see here, sorry, M3 is not connected. M2 was connected, and M4 is connected again. M4 is connected. M5 is connected, and M6 is not connected. Then M7 is connected, and then M10 is connected, right? So I get C. Similarly, I'll get B, I'll get A. So this is going to give me the application of ROM in order to have the lookup table for multiplication table of 3. So this in fact is also a special case of function realization. This is the input function, these are the input variables, this is the output function that I want to have, which is of uh, you know 4 different functions. Each of those output binary variable becomes a function, right? So using these lookup tables, you can have the waveform generation also. If what is a waveform? A waveform is the time plot, right? Time and amplitude. So if I take time as the input and amplitude as the output, that becomes the lookup table for a particular waveform, right? That may be irregular but periodic, that repeats after a certain interval of time. So that will become the waveform generation. So this is essentially a very useful circuit in the sense that a lot of things can be done. It is a code converter, it is a function realization, it is a waveform generator, it is the non-volatile storage, it is the non-volatile storage. That is why it can be used as the um, boot ROM, so that when the circuit, the computer is switched on, all the connections are there intact, right? So I can just pick those connections up, and you know correspondingly I'll get the word corresponding to the inputs that I'm giving, right? So these are some of the applications of ROM. Next, I'm going to explain the different types of ROM depending on their programmability. ROM is said to be a read-only memory. This is programmed, this is the simplest type, and this is programmed in the factory once and forever. Programming means blowing of those fuses. Those fuses were there, which take the connection to the OR gates. So once we supply what table we want to burn in a ROM, that is called ROM burning, that means programming the ROM. So what all fuses I want to keep intact, I won't burn them off, and whatever connections I don't want to be there, I'll supply a huge current through it so that the fuse is blown off and the connection is broken, it is disconnected, right? So that is called programming the ROM. But that happens once and forever in the factory. Once it happens, it is intact. That is why it is non-volatile, right? Then comes the next level of advancement, which is called programmable read-only memory. These are a special type of ROMs which may be programmed in the field. You don't have to necessarily get it programmed in the factory. They will give you a blank ROM. A blank ROM means all the fuses are intact. The fuses to the that provide the input to the OR gate, they are intact, but there may be a small device which can blow off some of those fuses to provide the required connection to the OR gates, right? So when the ROM has got the facility of being programmed in the field, that means in its application field, or the place where it has to be used, then it becomes a programmable read-only memory. So obviously the cost will go up when we move from a ROM to a programmable read-only memory. That will be costlier. Then there are erasable programmable read-only memory. Once you programmed it in the field, the application is over. Now you want to reuse that ROM for another application. So till now it was not erasable. Whether you programmed it in the factory or you programmed it in the field, that remains intact once and forever. But EEPROM, or erasable programmable read only memory, where you can put those fuses back through some ultraviolet exposure. There are ways. Through ultraviolet exposure, you can put those fuses back and then again program it by blowing huge current in order to blow off the fuses that you don't want to be there. So that becomes erasable programmable read-only memory. Such a ROM can be reused multiple times. Theoretically, it can be used infinite times, but practically, it goes bad after 4, 5, 10, depending on how good the ROM is. After those many usages, it may go bad. Then there is EEPROM. The difference between EEPROM and E square PROM or EEPROM is that over here erasure may be done through ultraviolet exposure, but over here erasure also can be done by electrical means. Just as we were doing the programming by electrical means and erasure by ultraviolet exposure, over here both programming and erasure both can be done using electrical means. Okay, so that becomes EEPROM. So versatility keeps going up when you move from ROM to PROM to EEPROM, then EEPROM or E square PROM. The versatility keeps going up, and obviously the cost also keeps going up. So these are the different types of ROM that you can employ. So after this, we will move to programmable logic array, PLA, as I said a little while ago, in which we are going to have not only the OR array as programmable, but also the AND array. That means you don't necessarily have to have a decoder. Okay, so that is called the programmable logic array. So let us see. This is the block diagram. You need not generate all the minterms, right? Generate just those minterms which are required, or just those product terms which are required. So you need not have essentially 2 to the power n gates, n and gates, if it is an n input device, right? You can have lesser number of gates. For example, the example that we took over here, we could have done using just 9 gates or 10 gates, to be precise, just 10 gates. Why employ extra 6 gates when they're never used, right? Or in this particular case also, these are never used. So these AND gates that are there inside this decoder are never used. So let us have the AND array also programmable, right? So that is why I'm saying with n inputs, there are only k product terms, right? Not necessarily all the 2 to the power n product terms. You know what I mean? Had it been a decoder, it would have 2 to the power n AND gates, right? but I'm not putting those many AND gates. In fact, k will be less than equal to 2 to the power n, right? So I'll provide to it all those AND gates, either n inputs true form or the inverted form of those n variables. Okay, I'll take the example, then things will become more clear. Let us see a generic diagram first. So since these n inputs are going to k product terms, so I should have n into k links, and the complement of these n inputs is also going to k product terms, so you have n into k links here also, right? So it will be those many links are there. Links, by links I mean the fuses, right? So I have those many fuses or links at the AND gate array also. Now these product k product terms, so k outputs are coming. Now these k outputs are going to m OR gates, right? Those OR gates that are there. So those OR gates are m, so k outputs, so I should have k into m links, right? K outputs, all those, each of those output is going to m different OR gates, so k into m links here. Now the interesting part is here that at the output I can get either f by keeping this link intact, or I can have f dash by blowing this off. So what does it mean? Till now, either in decoder realization of function or multiplexer based realization of function or ROM based realization of function, you necessarily have to have the canonical sum of product form. But when you move on to programmable logic array, it will be the minimized function that we will realize, because we have lesser number of product or the AND gates, and we have correspondingly we can have lesser number of OR gates. So it will more efficiently work on a minimized form of the function. So when it comes to minimization, we will see whether f is going to give me lesser number of product terms or f dash is going to give me lesser number of product terms. Whichever gives me lesser number of product terms, I'll use that. So if I'm using f, I'll keep this link intact so that I get f here and that comes out. The inverter is bypassed. But if f dash is going to give me lesser number of product terms, then in that case I'll blow this link off so that I get f dash here, and when it gets inverted I get f, right? So for m different functions, f1, f2, f3 and so on up till fm, I can decide which of these functions have to be in its true form through the fuse, or in its complement form when the fuse is blown off. So this is the block diagram. So both AND array as well as OR array is programmable. This is the block diagram of PLA. Now let us take an example, right? See, suppose I want to realize these two functions using PLA. If the same problem was given to me to realize using decoders or multiplexers or ROM, in that case, first I'll have to convert them into the canonical sum of product form. By now we know how can we do it. We'll have to AB dash dot C or C dash, AC dot B or B dash, then it will become the canonical sum of product form. But in PLA we will work with the minimized form itself, right? So ABC and its complemented version is available. Now see here, three inputs and their complements, and I'm just using three AND gates, right? If I can sense that this is a three variable function. If I had been in a ROM or a decoder or a multiplexer, there would have been as many as 8 AND gates, right? 2 to the power 3 is 8 for three variables. But I'm just doing with three AND gates. So I have saved 5 AND gates using PLA, right? So in this gate, I should have, how many links should be there? It says I should have n into k links, n into, so 2 into n into k, 2 into n into k. So for my case, 3 inputs, so 2 3s are 6, right? And 3 of them are there, right? So 2 3s are 6. Okay, so 2 3s are 6 is going to one gate, and the same 2 3s are 6 is going to the next gate, to the next. So total number of links over here will be 2 3s are 6, 3s are 18. So you can see 6 3s are 18. That is what I meant when I said, just hold on, when I said n into k links here and n into k links here, right? So now you see this AND gate is receiving not only A but also A dash, not only B but also B dash, and C and C dash. So all of them will be receiving A dash, B dash, C dash. Now it is up to me. I want to realize A B dash. So what I'll do is I'll keep the link corresponding to A as intact. A dash I'll blow it off, right? C also I don't want to have, because sorry, B I don't want to have. I want to have B dash instead. So you see this is B dash. So A B dash, these are the only two fuses. So what product term I'll get here, which is not the min term, this is the minimized product term. So I'll get A B dash here. Likewise, I'll generate AC here, and I'll also see that AC is common in both, right? AC is common in both. So one, you see this is A, this is A, and this is C. So I get AC here, which will be used at two places. And then another term that I must generate is BC. So you see this takes B and this takes over here C. So I get C here, right? Now I'll employ two OR gates, and these two OR gates, this will have AB dash or AC, right? The link corresponding to BC will be blown off because this function doesn't have BC. This fuse will remain because I'm realizing F1 itself. Okay. In the other case, the link corresponding to AB dash is blown off, so that is not connected. Only AC is connected and BC is connected. So I'll get F2 here, and this link will remain intact because I am generating F2 anyway. So this is how I can realize these two functions using PLA after saving lot of hardware or lot many gates, right? I have saved 5 different gates of 6 inputs each, right? Which would have been a case in the decoder or a multiplexer or the ROM. Okay. Now the next example that I'll see is the case where, so the next example will be the case where I'll try to minimize both F1 as well as F1 dash, F2 as well as F2 dash, and then I'll see which combination is going to give me lesser number of product terms, because each product term will require an AND gate. So I should check whether F1 F2 is going to give me lesser number of product terms, or F1 F2 dash, or F1 dash F2, or F1 dash F2 dash is going to give me the lesser number of product terms, because that is going to save me in the AND array. So let us take that example. Suppose I am given to realize these two functions, 35670247. So I told you that in PLA we have to minimize them. So at the time of minimization, I am going to minimize for both F1 as well as F2 dash. So I leave it to you. You plot F1 here and you see that F1 dash is, so I'll have F1 F1 dash, F2 and F2 dash, right? I have all these terms. So you can see F1 is 3567. So 0, 1, 2, 3, 4, 5, 6, 7. This is F1, right? So you can combine like this and you get AC plus AB plus BC. Likewise, you have F1 dash, right? So let me correct it. So I made the correction. I've put F1 dash sidewise. So f1 dash will be all those min terms which are not there, which is 0 1. So 0 1, and basically what all are zeros here, that we are going to combine, right? So this 0 0 0 0. When I combine them, this combination, it will give me b dash c dash, this particular thing, then a dash c dash, a dash c dash will come from these two, and then a dash b dash, that will come from here, right? Similarly f2 0247 0247, and I get b dash c dash, a dash c dash plus abc. This is not combined with anyone, so it will give me abc. I'll also do f2 dash, right? Now I see what all product terms I'll get. So I see that this table, this becomes the PLA program table now. This becomes the PLA program table, right? What it shows? It shows that, let's start from here. I should realize f1 in its complement form, which means this one, and f2 in its true form. So these two should be realized. Correspondingly, at the output of f1 dash, the fuse should be blown off so that I get f1 finally, right? So when I take these two, they are going to give me the minimum number of product terms. You can check for yourself. What are the terms? B dash, C dash. So I place it here. A dash, C dash, A dash, B dash. Right. Now you see B dash, C dash, A dash, C dash is common in both. So I just need to generate them once. A, B, C. Right. So now product number, term 1, 2, 3, 4. What is B dash, C dash? I'll say that the product term doesn't accept any input from A. It accepts the complement connection from B, and it accepts the complement function of C, right? B dash C dash. Likewise, A dash C dash means complement of this. B is not connected at all, and complement of C. A dash B dash means complement of A, complement of B, and C is not connected at all. ABC means all of them in its true form. So this will give me the three product terms. Now F1 is 1 1 1 here. This means B dash C dash plus A dash C dash plus A dash B dash, right? So this will give me F1 dash, and I am writing a complement here, right? And F2 is B dash C dash, so a 1 here, A dash C dash, so a 1 here, A dash B dash is not existing, so that will remain blank, and ABC is there, so a 1 here, and this is the true form. So this PLA program table is good enough to give me the logic circuit diagram of the PLA that realizes these two functions. So I'll essentially have four AND gates only, and two OR gates, right? So we will stop here. You can see that this PLA is the best implementation technique that we have seen so far, because it works on the most efficient realization of functions. You have to minimize, you have to see which combination is going to give me lesser number of product terms, so you save those many AND gates. If we were not saving those AND gates, you would have to have 8 extra gate AND gates, right? So it makes sense to minimize and then realize using a PLA. So we will stop here and we will continue from here in the next turn. Thank you very much.